Today we're going to talk about discrimination. Now, discrimination in statistics has nothing to do with the discrimination in everyday terms. We're not interested in being prejudiced against anyone. Discrimination statistics simply means the following: deciding between two or more sources, two or more things, two or more estimates, two or more parameters. In fact, the example that I'll start with is the dice problem that we had in the maximum likelihood experiment. That was a problem in discrimination. It had nothing to do with sex or race or religion, yet it was discrimination because it was deciding between which of the several pairs of dice caused the number that was rolled. So it was a discrimination problem. We had to discriminate between the different possible dice. That was a simple example of discrimination. There's another method, a better method than maximum likelihood for discrimination. Maximum likelihood can be used, and we will, and we've seen an example of it. And a better method, though, is to use more data. Maximum likelihood is weak. It only didn't do as well as it could have done. It should have done, that we'd like it to do. So we want to get some more data. And the way to use more data is to compare distributions. Now, we'll have to explain what a distribution in statistic is. Other names for it are frequency functions or histograms. So a distribution is sometimes called a frequency function. Sometimes it's called a histogram. If you see a histogram, you know it's a distribution. If you see a frequency function, you'll know it's a distribution. So sort of associate these words in your head. And we're going to compare distributions. What we're going to really do today is compare histograms. And what is a histogram? A histogram is a simple plot. Let's say I go out and I measure something, and that measurement can be 12 or 13 or 14 or 15 or 16 or 17. Those are the measurements I get. And sometimes I get 12, sometimes I get 15, sometimes 13, sometimes 17. Let's say I went out and I made 100 measurements, and I got 12 of them 10 times, and 13 of them 15 times, and 14 25 times. And I measured 15 30 times, and the measurement was 16 15 times, and it was 17 5 times, and no other measurements were made. Well, then 10% of my data is 12. 15% of my data is 13, 25% of my data is 14, 30% of my data is 15, 15% of my data was 16, and 5% of the data was 17. Don't confuse this set of numbers with this set of numbers. These numbers are the observations. These are the proportion of the time that I observe these numbers. If you say proportion of the time, you're essentially assuming that what's happening is I'm observing a number every minute, say, and this is a proportion of the time. I really mean the relative frequency. So if you're not observing them one a minute, but on an irregular basis, don't let that confuse you. Just make believe you're observing them one at a time when you mention relative frequency in time. This is 10% of the data is 12, 15% of the data. It really doesn't matter when they were taken, and so on. And this is called a histogram. You just make a box, proportional, heights are proportional. This is more than this by the same amount. This is more than that. This is the unit 5%, so this is 6 of them, this is 2 of them, this is 3 of them, and so on. And this is called a histogram. It's simply a bar chart, if you will, but it's scaled in such a way that the percentages represent the heights of the bar chart. That's a histogram. Well, how does that enter into discrimination? Let's take an example of discrimination. Deciding authorship. Deciding authorship. Let's say there's a book written, and we don't know who the author is. Maybe he used a pseudonym, and we want to figure out who wrote the book. And we've narrowed it down to, for simplicity's sake, two authors, A and B. And we want to see, is the style of the unknown more similar to A or more similar to B? Well, you could sort of most people can read it. If they're really different styles, you can tell them apart. But if they were really different styles, you wouldn't have narrowed it down to A and B. Evidently, the styles are pretty close, and just reading it, you can't tell. So we want to find some mechanism, some statistical mechanism for distinguishing, for discriminating between A and B. Who is the unknown author? Well, let's get rid of something which is really very simple. It's intuitively obvious. We'll do it first and we won't have to talk about it again. Something called a marker word. First you look for marker words. It may very well be that one of the authors was from England and one of the authors was from the United States, and this new book that we're trying to figure out who wrote has in it the word color, C-O-U-L-O-R. Well, C-O-U-L-O-R is the English spelling of color, and the Englishman will have had C-O-U-L-O-R in his book frequently, anytime he referred to color, and the American author would spell it C-O-L-O-R. And so you could distinguish which author was which simply by the use of that word. One author uses it, the other doesn't, and it's a marker word, a distinguishing characteristic. And if you find one of those, then you don't have to worry about it, because that tells you that's a telltale sign. For example, in the dice rolling experiment we did in maximum likelihood, if someone were to roll a 2 as the sum of one roll of the dice, or if you want 20 as the sum of 10 rolls of the dice. But let's say you had one roll of the dice, on the basis of that one roll I had to tell you which pair of dice it was. If you rolled a 2, there's only one pair of dice that can roll a 2, and that is the pair that has 1 and 1. That's a marker word. If you rolled a 18 with one roll of the dice, clearly it's the dice that went from 4 to 9, because only 2 dice going from 4 to 9 could give you an 18 on one roll of the dice. It's a marker word for that situation. That is, it's a dead giveaway. It's a sure thing. You know which one it is. There's really no problem there. Well, we're going to eliminate marker words. We're going to not say there are any, because then we don't need statistics really to find to discriminate using marker words. So let's assume there are no marker words, and let's try our discrimination using frequency distributions. What we have to do is to compare the distributions of common words. So what we do for each author is we pick a word, maybe when, say, W-H-E-N, a simple common word. And we take the author A and rip up his book into 1,000 words each. Maybe there's 100 batches of 1,000 words. We go through his book, every 1,000 words you draw a line and make 100 batches of 1,000. You can do more, but let's say for simplicity that we've done 100 batches of 1,000. And we count the number of whens in each of the 1,000. And there were 12, 13, 14, 15, 16, and 17 whens in those batches. 10 of the batches used when 12 times. 15 of the batches used it 13 times. 25% used it 14 times. 30% of the batches used when 15 times. 15% of the batches used when 16 times. 5% of the batches used when 17 times. Well, that's the distribution for author A for the word when. Well, let's do the same thing with author B. Here's author B. And we rip his book up, or draw lines every 1,000 words for 100 of them, or more if you like, but we have to get percentages, so it's easy to picture 100 batches, because then 5 batches he used when 14. He never used when 12 or 13 times in any of the batches we counted. And 15 batches he used when 15 times, 20 batches 16, 30 batches 17. Actually, all I care is that it's percent. 10% of the time he used 18 whens, and 15% 19 whens, and 5% 20 whens. Now, those distributions are characteristic of author A and author B. Now we go to the unknown, and we do the same with him. Assume we have a book from the unknown author, and we mark off every 1,000 words, 100,000, and we find that he used 13 10% of the time, and 14 25% of the time, and 15 25%, 16 30%, 17 5%, 18 5%. And now we have to decide, can you see that? Yeah, you can. Can you see which author is more like the unknown? Well, it takes a little looking. This author sort of goes up to about 15 is, and then comes down, so the 15 is the center. It's low, it goes here. This one sort of goes up around 17 and then comes down. So the center of this one's around 15, the center of this one's around 17. The unknown sort of goes up, flattens out, comes down quickly. If there's a center, it's closer to 15 than it is 17. And if you look at the overall pictures of the curves, this curve is a little closer to that curve than this one is. Or that is, this curve is closer to this than this curve is than it is to this. And so in this case, I would give the nod to author A. Now, that's my opinion. I think in this case it's fairly clear that A gets the nod over B. But it's not all that clear that that couldn't have been an accident if you had moved the line over a little bit, started counting in chapter 2 instead of chapter 1, you might have had a different distribution slightly. And so it's not quite so clear that author A is the author. So then you might want to do the same thing with the word then, say, or the word where, or pick several words. In fact, you would want to do it with several words and see. Now, if in each of the words author A got the nod over author B, you could feel rather comfortable that author A is the right author, and you've distinguished between them, you have discriminated between them, and author A is the correct author. And we had 2 A and B, but you could have A, B, C, D, E, and F. You could have as many as you like. Discrimination discriminates between several. Several can be 2, but certainly more than 2 is possible. So we would do that with several words. Now, what happens if there isn't enough data to make a histogram for the unknown? Now, generally for the knowns, there's no problem. But if there isn't enough data for a histogram for the unknown, we can use maximum likelihood. We've already seen maximum likelihood in the dice example, but let's use it here. Let's say we had only one batch of 1,000. It was an essay, and it was 1,000 words. And the mean number in the unknown is 15. 15 uses of the word where, or when, or whatever it is we're working with. So 15 is what we're trying to find. And now we look at the 2 distributions. This is distribution of A, and this is distribution of B. And we want to use maximum likelihood. Maximum likelihood says, look at the number. Now, which author A or B has more likelihood associated with the number 15? And the likelihood at 15 for author A is 30%, or 0.3. 30%. The likelihood associated with 15 for author B is 15%. See? 15% as opposed to 30%. Maximum likelihood says, pick the estimate, that is, which of these 2, this is the estimate, pick the one which shows the highest likelihood for the observed value. For the observed value, which one has the most likelihood? And in this case, the likelihood is higher for A than B, and so you would pick A again. Choose author A. That's the use of maximum likelihood. Easy enough. The idea of maximum likelihood was to see which gave the highest likelihood. And if you have a histogram, those heights are indeed likelihoods. They're probabilities, they're likelihoods, they're proportions. A proportion is a probability is a likelihood. And so the height of the histogram is the proportion of time that 15 was observed. It was observed 30% of the time in author A, only 15% in author B. Maximum likelihood says pick author A. Now, that's not as good as using the whole distribution. And one of the reasons for that is because we do have some problems in distributions and maximum likelihood. For example, what if we had an unknown author who had a distribution, say, looking like this? Now I'm switching, 18 is the bad one. Look what's happening. We've divided the book into 1,000 units, 100 units of 1,000 each. And when we measured, we got 15 14s and 15 uses, and 20% of the time he used it 16 times, and 30% of the time he used 17. But we didn't find any batch in which he used 18 whens, and 15 of the time he used 19 wins, and so on. Well, clearly this is a function of the fact that we drew lines on the thing every 1,000 words. Well, if we started a chapter later and drew lines, we might very well have seen 18s. In fact, if we just moved it a few words, perhaps some of these batches where there was 17 would have been less, and there might have been some 18s, and some of the 15s might have been less, and there might have been some of the 18s. The fact that there's no 18s here is sort of a fluke. It really shouldn't be 0, but it happens to be 0. Now, what happens if there's another one where the histogram might look like this, real concentrated around 13, say, and nothing out here, but at 18 you happen to get one, he happened to use 18 in one batch of 1,000, where generally he doesn't use 18. Well, that's kind of a fluke. If you use maximum likelihood and the mean were 18, the average were 8, the number he got, number of wens he used in his one little batch, the unknown, that is, the unknown used 18. And you would go maximum likelihood. You would say, okay, maximum likelihood here is 0. 0. Maximum likelihood here is 1%. Therefore, this is the right author. Clearly, if you observe an 18, this is more likely to be the author than this one. This author always uses very few wens, down here around 13. It was a fluke that he used 118 up here. I would not want to do that. Well, what do we do in a situation like this? What we do in a situation like this is not use the original histogram, but smooth out the thing. Replace the histogram with a smoother function. That would be replaced with that, this would be replaced with this, and clearly at 18 this is much higher than this one is at 18. Now, in order to smooth distributions, we use the normal distribution, and we're going to get into this later, but let's just preview it a little bit here. The solution to the problem is to smooth the distribution. That is, take that histogram and make a nice smooth curve. It'll become a bell-shaped curve like this. This might be one author, this might be another author. What you do, the way you do this, and it'll become clear later, is you estimate the mean and the standard deviation, whatever that may be, of the distribution. There's only 2 numbers you need from the data, from the histogram that you have. And then you replace the histogram with a normal distribution, the corresponding normal distribution. That is, the normal distribution with the same mean and standard deviation. And so a histogram looking like this would generally be replaced with this, and a histogram looking like this would be replaced with it. And even if it had a 0 in it, a little place where there was nothing, it would have a nice smooth shape. And then someone comes along and says, well, I observe a 16. Which is the most likely? You would simply find which of these distributions was highest at the point 16. In this case, it turns out to be the one on the left. The one on the left is higher than the one on the right. The one on the right is this high, the one on the left is this high, and so this is the author we would pick. What we did is smooth the distributions with a normal distribution, which we're going to get into at a later time. Okay, I think that about covers it for today.